I want to make a big heartfelt welcome to all of you. Thank you for setting aside 1 hour of today. I think we'll begin now, and I'm going to minimize my camera so you don't need to see me. We can just focus in on the slides. This is webinar number 106, which we are also calling our final review of our MOOC, our massive open online course, also called Motorized Pulley University. We are glad so many folks have decided to spend an hour with us. Thank you for that. The host for this webinar is Rulmeca Corporation in Wilmington, North Carolina. As you can see, we're a major supplier of motorized pulleys to the U.S. materials handling market. We were founded in 2003, and today's presenters are Brian Vrablik, our Director of Sales and Marketing, Steve Forbes and Zach Lehman from our sales department, and myself, Mike Gowinski. All of our mics are active, so any of the four of us can speak at any time. If I forget to say something, any one of them will jump in. However, their primary role in the next hour will be to pay attention to the chat feature. None of you participants will be able to speak, and that's unfortunate. However, you can communicate with us. So feel free to use your chat feature to ask questions or make comments, and Brian and Steve and Zach will respond to you. And at the end, we will have these three gentlemen tell us which questions need group attention, in other words, worthy of everybody hearing answers for. So I'm hoping that we'll time this just right and have 50 minutes of slides and 10 minutes of discussion at the end. As I said previously, this is the final review of the second semester of our Conveyor Drive University. And pictured before you, you can see on the left, the first semester consisting of 6 modules of videos complemented with Microsoft Forms quizzes. Thanks everybody for your participation in that. This is 6 hours of video watching, believe it or not, 6 hours in the first semester, and something like maybe 2 hours of quiz taking to fill in the answers to the quizzes. We reviewed that. We went through the first semester on October the 7th. Today is the review of the second semester. And if you looked at all of them, and we know that some of you have, that's 3 hours of video watching. We've looked at the answers to your quizzes. Thanks for spending that time. And I hope that we will be scratching where you're itching. We're trying to do in 1 hour what we would ordinarily take a half a day to do. Ordinarily, our motorized pulley training is a day and a half here in Wilmington or some other venue, but usually Wilmington. We've had to cancel them this year because of COVID concerns and replace them with our online university. So today, as I said, we'll be looking at the second semester topics, namely, and we're only going to hit highlights. We can't possibly squeeze into 3 hours of video into 1 hour, but we'll be talking about the highlights of how to calculate a conveyor drive pulley, how to calculate power required for the pulley, how to calculate belt cleaner drag. We'll talk for a bit on hopper feeders. That's one of our most popular videos. It's been watched tens of thousands of times. So we'll spend some time on hopper feeders. And then we will also go through what we call our install, maintain, and troubleshoot lecture. We'll have some highlight slides from that. So the 7 items on our agenda are conveyor belt tensions and required power, how to calculate that, belt cleaner drag and required power, how to calculate that, 2 segments on hopper feeder drag and required power, and a few comments on how to calculate hopper pressure relief, and then 3 segments on installation, maintenance, and troubleshooting of conveyor drives. And of course, since we're a manufacturer of motorized pulleys, we'll be using motorized pulleys in most of our illustrations through the hour. We start with a peek at a standard conveyor to explore tensions. The tensions which are most relevant to today's talk are TE, also called effective tension, and T2, also called slack side tension. We are using the CEMA historical methodology in today's discussion. Our company, as you most likely are well aware, is an international company with affiliates in 24 countries. At our company, our group headquarters in Italy, the fellows have developed a new methodology for conveyor power calculations based on both the DIN for our European colleagues, DIN standards, and the CEMA universal method that's based on edition 7 of the CEMA design manual. What we'll be using today is the nomenclature from the historical method, which was developed in the 1950s, and we continue to use to this time. Once we calculate TE effective tension, then we know what power to supply to make the conveyor work. This conveyor shows typical carrying idlers, return idlers, a drive pulley in its instance located at the head, a belt cleaner located at the head, and then some other idler pulleys, such as the ones within the counterweighted take-up area and in the tail section. Notice that T2, slack side tension, is thought to be equal throughout the entire length. So once we calculate T2, we can assume, like a belt that you might wear around your waist, it's everywhere. It can be felt everywhere. TE, in the case of a head-driven conveyor, will be in the immediate vicinity of the head pulley. This is the historical method for calculating effective tension TE. CEMA calculated back in the 50s, or developed back in the 50s, a way of calculating a method to overcome friction in a conveyor system, how to overcome gravity, and how to overcome momentum. So these three segments are included within the historical methodology. And our program using the historical method is downloadable from our website. You can also have access to the universal method, which is an online portal type program available through the group anywhere in the world. And you can access it through our website. Let's talk about T2 slack side tension for the next couple of minutes. There are two types of T2 that need to be computed, one of which is T2 required to prevent slippage of the belt on the pulley surface. This is the simplified equation here, effective tension times the CEMA factor. The CEMA factor can vary from a number as small as 0.8 to as high as 1.2. I won't go through the trouble of explaining all of that, but the CEMA methodology lets the user of the program be aware of what slack side tension is required to prevent slippage. The other equally important slack side tension to compute is the one required to resist sag. You cannot allow the conveyor belt to sag beyond a small amount between the troughing idlers. Typically, the area of least tension is in the loading zone, and that typically is near the tail of the conveyor, as pictured here on the left. If the sag is too large, then the problem would be spillage in that zone, and it could either be a nuisance, where you'd need to clean it frequently, or a disaster if it completely fills the tail section and stalls out the belt. So it's essential to calculate T0, the tension required to prevent sag, and T2 is then developed, as you can see here. T2 is developed, as you can see here. That's the sum of T0 plus the weight of the carrying out and or return strand of the belt for a sloped conveyor, and the tension required for the empty belt to overcome return idler friction. You either add or subtract depending upon whether your conveyor is inclined, has an incline or a decline. Once we know each of the two T2s, the one to prevent slippage and the one to prevent sag, we select the larger of the two as governing, and we use TE to calculate power, as you can see in the top equation here. We know that TE, effective tension in pounds, multiplied by V, which is belt speed in feet per minute, comes out to be a certain number of foot-pounds per minute. And since we know 1 horsepower equals 33,000 foot-pounds per minute, once we have the product of these two numbers, we know how much power to supply in the drive system. To finish the discussion on the tensions, we select the larger of the two tensions. Let's say, for example, T2 required to prevent slippage is 1,000 pounds, and let's assume that T2 required to resist sag is 800 pounds. We would certainly select the T2 of 1,000, and we would select a counterweight, which in this example would weigh 2,000 pounds, so that we can have equal and opposite force to the pulley in the counterweight to take up of 1,000 pounds. So having 1,000 pounds scattered throughout the conveyor helps us with our slippage and our sag problems. And we need to remember when calculating T1, we'll come back to this later, T1 is the maximum tension in the conveyor belt. On an inclined conveyor such as this one, it's near the head. T1 is the sum of slack side tension plus effective tension. Now for a couple of minutes, let's discuss one component of effective tension. And one of the components is the drag required to overcome belt cleaner, the pull required to overcome belt cleaner drag. CEMA recommends the equation of the CEMA factor multiplied against the width of the blade times the number of blades. And they suggest that factors from as small as 2 pounds per inch of blade width to 14 pounds per inch of blade width could be used. If unknown, CEMA recommends using 5 inches per pound of blade width. Rulmeca suggests that to be conservative, you simply use 5 pounds per inch and multiply that against the belt width. Rather than, in our example here on the left, you can see what might be a 30-inch wide belt and perhaps a 24-inch wide belt cleaner. Let's simplify things and simply multiply 5 pounds per inch against 30 inches of belt width, and we multiply that product against the total number of cleaners installed. That's a simple and safe way to come up with the amount of drag which you need to overcome in your drive system. Now let's turn our attention to 4 types of hopper feeders. As I said, these hopper feeder videos, since we posted them a couple of years ago, have gotten thousands of views. So it seems to tell us that there's a requirement for people to get guidance on how to do a proper calculation of a hopper feeder conveyor drive. We'll look at material storage, material blending, material receiving batch loading, and material metering. These examples on the left show iron ore, and on the right, wood chips. The silos on the left and the hoppers on the right are simply vessels to contain material so as to have it on hand when it's needed in the process. This example shows material blending, and this is the sort of thing that might be seen in a typical batch plant near a highway, along the side of a highway at a construction site. The various pant legs in this particular hopper might contain various grades of aggregate, different sizes of aggregate, different types of sand, and so forth, all of which can be blended together to make the recipe required to build the road. And here we have examples of how a hopper might be used to receive batch loading. The example on the upper left shows that the hopper is simply the intermediary in between the batch unloading of this barge using a clamshell and the continuous takeaway by the dock conveyor. The hopper serves as the intermediate spot. Here's an example of a rotary rail car dumper dumping batches onto a continuously taking a conveyor which is continuously withdrawing material. Likewise, a front end loader and truck dumps in a mine. And finally, material metering. A hopper may be used to provide material at various rates. In this example, we have 2 motorized pulleys in service, each of which is on a conveyor, which is tied in with an ultrasonic probe and a variable frequency drive. The ultrasonic probe sends a signal to the variable frequency drive, which then in real time either speeds up or slows down the conveyor belt so as to choke feed the crusher. For optimal performance, the crusher is supposed to have the material at a certain level, and by metering the material from beneath the hopper, the operator can accomplish that. Now let's draw an important distinction between two types of flow. One would be continuous flow, and the other is metered flow. So I asked the question, if we have an example where conveyor A is feeding conveyor B continuously, and conveyor A is handling 1,000 tons per hour, and it has a belt speed of 100 feet per minute. If we have a belt speed on conveyor B of 200 feet per minute, what is the output? Is it 2,000 tons per hour? The answer is no. The answer is 1,000 tons per hour, because in a continuous flow situation, what is coming in, the rate of material coming in equals the rate of material going out, regardless of the belt speed of either belt. However, when we look at flow from a metering hopper, assuming that the output is unrestricted, if we start out with an unrestricted output of 1,000 tons per hour on a 100 foot per minute hopper feeder conveyor, what would be the material handling rate if we speed up that conveyor belt to 200 feet per minute? And the answer is 2,000 tons per hour. The handling rate is linearly proportional to the belt speed within certain considerations. If you make it 10,000 feet per minute, obviously it's not going to work. But within the normal parameters of conveyor design, conveyor handling rate and belt speed are linearly related. Now let's take a more careful look at how we would come up with the force required to overcome the drag in a hopper. On the left, we have an empty hopper. In the center, we have a full hopper. Our objective is to calculate F, the amount of effective tension that the drive needs to supply to the conveyor belt to overcome drag within the hopper. In order to accomplish this, it's essential to understand the concept of arching theory. Arching theory tells us that we only need to concern ourselves with the active volume of material in the hopper, assuming that all of the rest of the material will be self-supporting. In other words, the inclined hopper walls are going to be holding up most of the material, whereas we need to concern ourselves with the active volume, which is going to be pressing down on the conveyor belt. So what is the force required to overcome the material in the active volume? Let's have a look at how to calculate that. We simplify this technique by saying, rather than attempting to calculate the volume of a parabolic shape, we simply approximate that shape with a prism, meaning a rectangular shape. And we say that the prism is defined, the volume of the prism is defined by its width, which you can see here, and its length, which you can see here, and its height. And we always assume that the height is 3 times either the width or the length, whichever is smaller. So we assume that the height of this prism is 3 times either the width or the length, whichever is smaller. Once we calculate this active volume in cubic feet, and we know the bulk density in pounds per cubic feet, we know the weight of the active volume. And then comes the secret sauce. We simply apply a factor of 0.5 to approximate the cutting force required to overcome that active volume. So first we can calculate the volume. We determine the weight of that volume by multiplying by bulk density, and then we multiply that weight by 0.5 to come up with the, in imperial units, the number of pounds that the conveyor drive must supply to overcome the drag. A very important concept to understand is pressure relief. It is possible to decrease the amount of power required to drive a hopper feeder conveyor simply by restricting the opening. Of course, it would be a problem if it was restricted too much and it would plug. So a certain amount of reason needs to be used when figuring this out. We have an example on the left of a hopper at a ship loading terminal, and you can see this bird's eye view of an inverted angle or a tent. This operator changed a single opening hopper into a 2 opening hopper. How do we calculate the active volume in this case? It's exactly the same as before. We simply assume that the length equals the length defined between the hopper edge and the tent, and the width, in this case, if one tent was put in, the width would be equal to the width without the pressure relief, and the height is simply 3 times either the length, L prime, or W, whichever is smaller. Once we know the volume, we can calculate the weight, and then we use the 0.5 factor to figure out how much drag is required. And lastly, the same concept can be used to change a single hopper opening into a 4 opening hopper opening. And keeping in mind that the height is 3 times the smaller of the width or the length, when we can reduce the height by changing the width or length dimension, that's the trick into reducing the amount of drag that a hopper would be placing on the hopper feeder conveyor. I realize that was very quick, and I'm trying to compress into a few minutes what our video takes 20 minutes to explain. Now let's turn our attention to some conveyor drive installation tips. We'll look at 4 of them: drivetrain orientation, mounting bracket location, radial load caution, and a reversing conveyor control caution. When considering the installation of a Rulmeca motorized pulley, it's essential to realize that there is an up and a down. And our smaller pulleys are stamped with the word UP on the shaft to indicate the 12 o'clock position. If we imagine the pulley as the face of a clock, the up should be either at the 12 o'clock position or at the 3 o'clock position, and that is defined by the direction of the belt. So if the direction of the belt, as you can see with my arrow here, is toward 3 o'clock, then it's perfectly acceptable to put the up indicator in the 3 o'clock position. It's not acceptable to put the up in the 9 o'clock position, and it's not acceptable to invert the motorized pulley. These are all the small pulleys, 16 inches in diameter and smaller. And the 4 circles at the bottom, this, by the way, is extracted from our installation guide. Our cast iron brackets, which are the 360-degree cast iron brackets, also have the same restriction. We don't stamp the word UP on the shaft anywhere, but these pictures show which is correct and which is incorrect. To mount a motorized pulley on a vertical surface, it's no problem if you do it in this manner. To mount the pulley on a horizontal surface, this manner would be just fine. It would be incorrect to suspend the motorized pulley from a horizontal flange in what you might call the upside down position without advising us. You certainly can suspend it from above. However, it has to be configured in a special way at no extra charge. We simply reorient the drivetrain to meet the needs of the operator. And let me explain why this is important. There's 2 important things to remember. On the left is a cutaway drawing of one of our smaller motorized pulleys. This one happens to be 16 inches in diameter. And on the right is a cross-sectional diagram of one of our larger ones, 20 inches or larger. This happens to be 24 inches. Notice, and both are in the correct configuration. In other words, the up arrow is in the up direction. Notice in a small motorized pulley, the gearbox is down in the oil. And as I mentioned before, you can incline it 90 degrees, and that would mean the gearbox is half out. However, in the case of the big motorized pulley, when it's mounted correctly, the gearbox is up out of the oil, and it's also permissible to have it half in. We've learned over the years that it's essential to configure these gearboxes in this way so as to prevent frothing of the oil. And you don't need to worry about this gearbox running dry because the geared rim is like a water wheel pulling oil continuously up to lubricate all of the teeth and all of the bearings in the box. Here's another thing to keep in mind. when thinking about proper drive orientation. I have this pulley, let's say upside down, and I've tried to depict excessive radial load. If this pulley was subjected to radial load in excess of what it's supposed to handle, it could be a problem. And why would that be? Notice that the force of the belt, which in this case is going from down below to up above, would be resisted by equal and opposite forces supplied by the conveyor frame. The thing to point out here, the thing to understand here is that the gearbox, if you can see my arrowhead, the gearbox would be allowed to be torn open. Whereas if the pulley was inverted, the gearbox would be compressed. The whole point being that when the pulley is properly oriented, you are providing yourself extra strength to resist stress from excess radial load. Let's have a look at several mounting orientations. Here we have a large motorized pulley mounted on a horizontal surface, another horizontal surface, and here we have our smaller pulleys, in this case mounted on a vertical surface and on a horizontal surface here. In addition to paying attention to avoiding excess radial load, it's important to pay attention that the brackets be mounted flush against the shoulder on the shaft. You can see a properly configured mounting bracket on the left and an improperly configured mounting bracket on the right. Notice that the mounting bracket was not pressed flush against the shaft on the shoulder, and this is a labyrinth type motorized pulley, and grease was allowed to escape, making a mess. A simple problem to fix. Tap it inward and you're good to go. Let's talk a bit more about what I mentioned briefly earlier, and that is radial load. Radial load is the vector sum of the belt tensions which act on a motorized pulley. We described T1 previously, and you may remember that T1 equals effective tension plus slack side tension on the carrying strand. To that, we must add T2 on the return strand to come up with a vector sum, which looks like this, equal to T1 plus T2. A simple number to calculate and a very important number to double check so as not to allow any drive system to be overstressed. Here's an example of a motorized pulley, of an idler pulley, which was overstressed. This one was purchased and installed. It happens to be our 500L idler pulley, and it has the capability of withstanding a radial load of 10,000 pounds. And it failed very quickly because it was incorrectly installed on a bucket wheel reclaimer in the discharge position, and the actual radial load was 18,000 pounds. So the fix to this problem was to install the right thing, which in this case happens to be our model 630 idler pulley. A good example of radial load failure. Notice that the failure mode was the lagging came off in no time, and the bearing housing broke off. The weld between the bearing housing and the end housing failed. I hate showing pictures of damaged pulleys, but how can we learn if we don't look at damage? We can learn how to avoid damage by looking at past problems. This is an example of a Model 630 installed in a shuttle conveyor, which was a reversing conveyor handling iron ore for a 60-inch wide belt. It charges, as a matter of fact, it charges the storage silos that you saw previously. A soft start or a variable frequency drive were suggested, however, not installed. And unfortunately, the conveyor was not brought to a complete dead stop before reversing direction. And the result of that was a torque side torsion failure of the shaft, which you can see pictured here in the gearbox, attached to the gearbox. Torque side shaft failure when the conveyor direction was changed without bringing the speed to zero in between changes. Let's turn our attention to a few maintenance tips. We'll be exploring the topics of external temperature monitoring, current draw monitoring, vibration analysis, tribology, and just a couple of minutes on what we think will be a growing idea, which is internal temperature monitoring. External temperature monitoring can be crude, easily done. It can be done on whatever schedule the operator thinks is best. We recommend that if a laser thermometer is used, the external temperature be measured at the midpoint between the shaft and the pulley lagging. This is the spot of highest temperature on the external temperature of the motorized pulley. A temperature strip can be used. Here you can see one which was affixed to a motorized pulley. And a temperature strip is nothing more than a device which stains itself at the maximum temperature achieved. So if an operator were to have a look at this temp strip once a month and sees every month it's staying at 170, that's a crude way of making sure that the temperature is behaving itself. And by the way, 170 is no problem for a motorized pulley. If, however, the operator were to come out and see it stained at 180 or 190, whereas it's been 170 for 6 months, this is an indicator that there's a problem which should be explored. External temperature monitoring can also be done using infrared spectrometry. Some of you may be well acquainted with this, in fact, better acquainted than we are, and some may not. So for those of you that are hearing this for the first time, we can tell you that infrared spectrometry is a great way to look at what's happening, at least externally on the motorized pulley, to come up with some conclusions about what might be happening on the inside. The way the spectrometry picture works is that the lowest temperature shown, which is dark blue, in this case is 88 degrees Fahrenheit. The highest is 140 degrees Fahrenheit, and it's white. So that tells us that the bearing housing in the center of the end housing was the maximum here, and that was 140 degrees Fahrenheit when it was checked. Now I can turn our attention to current draw monitoring. This was actually submitted to us years ago when a customer was trying to come up with a reason for peaks in amp draw. Eventually, an inspection on site determined that there was a material buildup between the slider bed and the belt, which was causing this periodic spiking in the current draw. I'll explain in a minute the relationship between horsepower and current draw, but it's obvious that a spike, such as you see here and here, could be a problem. Notice that the y-axis shows 100 amps at the top, 80 amps here, and across the x-axis we have time. So this conveyor was periodically spiking the current draw on conveyor BC-2, which is the blue curve. Now I'd like to turn our attention to a vibration analysis. This picture shows two great spots where a transducer can be fixed from time to time. In other words, it can be permanently attached or it can be attached as needed. We're coming to a case where a transducer was attached on a monthly basis in this in this location here. The point is to have a consistent spot for the transducer to rest so that consistent readings would be resulting. This cross-sectional diagram shows the items within the motorized pulley which will cause vibration, and they consist of a certain number of bearings and a certain number of gears marked in red. When requested by customers to prepare their motorized pulley for vibration analysis, we provide this kind of data. We don't ordinarily provide this amount of data with a motorized pulley, but would be glad to do it when we know that a customer wants to set up for vibration analysis. Look, for example, drawing position 9 happens to be the rotor pinion, and it consists of a 23-tooth gear in this particular one. The input wheel, on the other hand, is 80 teeth. A vibration technician would be able to understand the relationship between the number of teeth in a gear or the number of rolls or balls in bearings and the vibration signature. Here you see shown on the left a diagram of 2.5 years of vibration monitoring, which was done on a monthly basis. On the right, you can see the spot where the transducer was consistently affixed on a monthly basis on our model 630, on a model 800. What I'm trying to show here is that after 2.5 years of consistent readings, a trend was observed on one of the amplitudes. The amplitude increased on a certain frequency. In other words, we saw an unusual behavior of the amplitude on a particular frequency, indicative of some sort of a problem. Actually, using vibration analysis, this pulley was pulled out of service, a spare was put in, the pulley returned to us here at Wilmington, North Carolina, and upon disassembly, we discovered that the load on the pulley was so much less than was originally intended. The bearing was too strong, and the fix was to put in a different type of a bearing in which the load would be more matching to the design of the bearing. The bearing that was installed originally was so strong that after 2.5 years, the rolls began to slip rather than roll. That, of course, is a bad thing for a bearing. And our last bit of maintenance technology I would like to show you is here. On the left, you're looking at some infrared spectrometry, and on the right, a graph which depicts internal temperature of a motorized pulley. This was a particularly challenging application because what you're seeing on the left is a hopper being charged with 25 dumps in a 5-minute cycle. Hot material, you can see how hot it is, 120 degrees Fahrenheit. So hot material was being charged directly onto a hopper feeder conveyor, 25 dumps in 5 minutes. Then that, and by the way, the conveyor is withdrawing the material out of your monitor. So imagine the material is coming into your direction very slowly at 2 feet per minute. And the full complement of material would be dumped in approximately 20 minutes. So 5 minutes to fill and then 20 minutes to empty at 2 feet per minute. And we were all concerned that the pulley might not be able to cool itself. Beyond the scope of this slide is the fact that we recommended an external air plenum to blow air over the face of the motorized pulley. The point of the slide is to show you that over time, we were monitoring current draw. So hopefully you can see my arrowhead on my cursor. In 5 minutes, the temperature of the stator would increase as the conveyor belt was completely filled. And then in the next 20 minutes, the temperature would decrease as it was slowly discharged, only to be filled again in 5 minutes and then emptied in 20 minutes. Down below in blue, you see the ambient temperature, which was quite a pleasant environment as far as ambient air. It was in the 70s in October of 2018. I beg your pardon, in December of 2018. What's the point of all this? The point of all this is that our maximum temperature measured internally was below 120 degrees Fahrenheit, meaning that this thing should work for a very long period of time with no problems through this entire cycle, in spite of the fact that the belt speed is so slow. The internal temperature of the motorized pulley can easily hit 240 degrees Fahrenheit with no problem, plus or minus 20 degrees with no problem. Now, I'd like to spend some time discussing electrical installation and some troubleshooting tips. We'll look at the relationship between power and full load amps. We'll look at overcurrent plus thermal protection, and then have a peek at some burn motors. This graph shows our portfolio from our small model 80 LS on the left to model 500 LS on the right. And it shows the relationship between horsepower, which is the red line, and full load amps, which is the solid blue line. It also shows no load amps, which is the dotted blue line. This graph allows us to focus and maybe see the numbers better on the model 220 to 500. As a matter of fact, our example later is going to be on this exact model, which is our model 400. You can see model depicted on the right right-hand y-axis, model 400. A model 20 horsepower, amps and horsepower is on the left. So 20 horsepower, model 400 draws 23.5 amps. Notice also that this particular 20 horse model has a no-load amp draw of approximately 12.5 amps. So a lot of stuff is shown on this graph. The point of it is the direct relationship between power and amp draw. An AC squirrel cage induction motor, 3-phase, is not capable of protecting itself from self-destructing. So if a 20 horsepower motor is installed and 20 horsepower is required, then things should be copacetic. However, if the conveyor requires more than 20 horsepower, that 20 horsepower which has been installed, the 20 horsepower motor, will attempt to provide more power. And the only way it has of attempting to provide more power is by drawing more current. And current is the enemy. When current exceeds what the motor is designed for, that is where a problem comes in. So let's talk about how to protect the motor. We build all of our motorized pulleys with thermal protection switches in the stator head. Here's one of the three. And all AC motors, of course, need to be protected with a current overload switch. On the right, you'll see a current overload switch with a variable overcurrent setting. So let's just say we have a motor which draws 4 amps, full load amps of 4. So this would be the correct setting. If that conveyor, after a few weeks or months, decided to trip out every once in a while, it would be a terrible idea to change the overcurrent setting to 5 amps or 6 amps, because you're negating the overcurrent protection that that motor needs. If the full load amps are 4, that means the motor is designed to carry 4 amps continuously. It can carry in excess of 4 amps. As a matter of fact, any design C AC squirrel cage induction motor is going to have an inrush current of 6 times FLA at startup for a few seconds. However, to change the overcurrent setting from FLA to some higher number is a terrible idea, because the motor cannot sustain above FLA indefinitely. This circuit diagram shows 2 circuits. It shows the power circuit, the 3 bold power lines coming from right to left, and then the thin 110 volt normally closed control circuit, which controls the conveyor. As we go from left to right, you can see that this normally closed control circuit has an on-off switch in it. It has a belt misalignment switch. It has an emergency pull cord switch. All of these switches are wired in series and are intended to be closed in order for the conveyor to be working. As we work our way around the circle and we work our way to the motor starter, here you have a symbol for what I showed previously. This is the overcurrent protection switch, which should pop open if FLA is exceeded. If current flow exceeds FLA, the switch will open and automatically cut power, in this case 3-phase power, to the motor. Also shown on this diagram, and this is our sermon for the day, we strongly believe that our thermal protection switches should be wired into a normally closed control circuit. It is possible to drive a motorized pulley without connecting the built-in thermal protection switches to a control circuit, but we would say it's a bad idea because it's giving you an extra layer of protection. Overcurrent protection is one thing. Temperature protection is something completely different. And to take advantage of what we offer, something we certainly recommend. This circuit diagram shows nothing more than 3 thermal protection switches wired in series in the stator head, brought to a common pair of terminals within our junction box. And this is what the thermal protection switches look like. In the background, you can see a stator head. And this is what a motor looks like when it has been stressed, when it has been overloaded. Uniform burning, all phases are burned. If we have a situation with inadequate power, We should measure amp draw, make a physical inspection, recheck the operating parameters, and if necessary, do power calculations over again. A variety of things can happen over time. You can have accumulated carryback under idlers. Belt cleaners may have been added. I talked previously about a belt cleaner adds drag to a belt. If a conveyor was originally designed to have one and an operator decided to put in 3 to clean it better, that doesn't happen for free. It's possible that more power is required. Skirt bore seals might have been revised. Carrying or return items might not be turning. These are all reasons for a drive to perhaps have inadequate power. And so as to not miss this, it's possible that pressure relief, this is a diagram of a hopper, if hopper pressure relief had been added, however, if the tent had fallen out, that could overload the conveyor belt, and we require a physical inspection to verify that. Other things to check for in the case of an overloaded motor would be, did you increase your handling rate? Are you now handling 2,500 tons per hour, whereas previously you were planning on 1,500? Or did your material change? Did you go from, say, handling coal to handling a more dense product like rock or iron or something like that? Did weather conditions change? Did you relocate a system which was developed for warm weather, and now it's been deployed in a cold area where belts are much harder in winter, harder to turn in winter, cause more power in winter? Did you change your belt speed? Did you change the inclination angle and so forth? These are all things that should be checked, and these are all things which were covered in the second semester of our training. Now let's have a peek at a motorized pulley, which was supposedly too weak. We were told that this is years ago, a 20 horsepower motor was too weak. And so with the permission of the operator, we installed a current monitoring device. And you can see over this 24-hour period, this 20 horsepower Model 400 3-stage model was permitted to exceed FLA repeatedly for extended period of times. It would be no problem if the 23.5 amps was exceeded, 23.6 amps was exceeded for a few seconds to start up the conveyor every few hours. But notice that it was allowed to exceed it for extended period of times. And the result was what you saw previously, a uniformly damaged motor from overstress. In other words, installing a 20 where something different was required. And yes, the correction to the problem was the installation of a 25 horsepower conveyor drive. Here is a picture of a different type of motor damage. The purpose of showing you this, we have plenty of them, but this is the the second one I'm showing, the last one I'm showing. When we take these things apart, it's not difficult to diagnose what the problem may have been. This is certainly not an overloaded motor because the burn is concentrated in one area. This would be this localized burn would be typical of overvoltage, something that could happen due to a lightning strike, or it can happen if a VFD was controlling the drive and the output of the VFD wasn't filtered, and a resonance-induced voltage spike actually happened between the VFD and the motorized pulley. On the right, you'll see what the stator should look like, and on the left, you see what it looks like when you zap a 230-volt motor with a 460-volt power supply. I hope you don't feel rushed. I know I talked really quickly here, but I tried to cover the essence of what our second semester included. I talked about belt tensions and calculating required power. We talked a bit about belt cleaner drag, some features with hopper regarding arching theory, how to calculate drag, how to relieve that drag by installing pressure, and then some installation, maintenance, and troubleshooting tips. And at this point, I'm going to ask Brian, Steve, and Zach if you guys have been addressing any questions or comments as I've been speaking.
Yeah, a couple that have come in, just checking to make sure they knew where to get some of the information from. So I posted
Okay.
the link to the online courses.
Great.
And
It's a perfect segue, Brian, and I'll put up a slide and allow you to continue to talk.
yeah, so certainly, you can find all of this information is on our website, rulmecacorp.com. And then our YouTube channel, you can just search Rulmeca Corporation in YouTube and our channel will come up. Yeah, I would encourage you to subscribe to our YouTube channel and you'll get notifications when we post new videos. I have a host of videos that are we plan for next year, and we will continue to do webinars like this on a fairly regular basis next year. So stay tuned for that. And other than that, we certainly appreciate everybody that showed up. And if anybody's got any questions, don't hesitate to reach out.
If you have any more, this is the end of 50 minutes together, ladies and gentlemen. And we always try to leave 10 minutes at the end for some give and take. And rather than rush things and cut it off, we're going to leave the chat feature open so that you can express yourself to Brian, Zach, and Steve. And I just want to give another pitch to what Brian mentioned, which is an upcoming video. Our next one is going to be addressing the topic of using variable frequency drives with AC squirrel cage induction motors, particularly ours, to help with some of the nuances of using VFDs. Just a sneak preview, I can tell you that our motors within the frequency spectrum give constant torque. They provide constant torque. However, horsepower and frequency are linearly related. And so we have a bunch of things to say about rates, tons per hour, feet per minute, cycles per second, for example, 50 hertz versus 60 hertz or whatever. So that's the thing that we're scratching around with now. And hopefully within the next month, we'll have that thing launched on our YouTube channel. We're targeting a 10-minute time frame to go through that.
So another couple of questions that have come in from someone. So the question was asked about service factor, and our service factor that we use is 1. So when we size our pulleys, our service factor is 1. So that our nameplate service factor is 1. So when we sell you a 10 horsepower motor, you get a 10 horsepower motor. We expect you to use it as a 10 horsepower motor. Some motors will be 1.15 or 1.2. That means if they sell you a 10 horsepower motor, the manufacturer is literally expecting you to use it at 12 horsepower. We don't do that. The way we manage horsepower requirement is if an application needs 9 horsepower, we make it 10 horsepower and we can supply that, but we might also supply it 15 horsepower just to give us that safety factor rather than use a service factor, eat up all of the service factor, which is 1 in our case. So that's how we manage horsepower and service factors and power factors on our end.
To say it in a slightly different way, as much as possible, we love to get involved with our customers, our end users, our engineers, and talk over this exact thing. If you need 9 horsepower, what's the likelihood that it would be 11 one day? Are you intending to keep your idlers clean, or between us, do we know that they're really not going to be cleaned well? Some soul searching has to be done up front. If we know that normal housekeeping is not going to take place, or if we suspect that the operator quote might cheat and try to move 1,500 tons per hour, even though we told you 1,200 tons per hour, it's nice to get that all on the table up front. And we would say that's what we like to do rather than sticking in some more copper and saying everything's fine because we have a higher factor. So that's my 2 cents worth on it. We're all about calculating power, and we're all about trying to estimate operating conditions as best we can. And if they're going to vary in the wrong way, let's do what Brian just said. You need 9, let's put 15 horsepower in.
So another question that came in was about, using the same calculations for what we call unit handling conveyors. In theory, the calculations are the same, but we do have a different calculator on our website, and I just posted that to the question section. So you can grab that from our website also. It's a little bit more rudimentary than the CEMA bulk handling version that we use, but it will calculate belt pull based on conveyor length and conveyor speed and pounds per foot of belt, and whether or not it's a roller conveyor or a slider bed conveyor, and what kind of belt you're using and that sort of stuff. So we do have a different version of belt pull calculation.
On that subject, I'd like to add that we have a couple of videos we put together for horizontal unit handling and also incline unit handling, and for that matter, also metric. Typically, we talk in imperial units, but we put a metric version together, which surprisingly is very popular. We put the thing together when we all were working from home due to COVID, and just saw the views of it explode. So that's kind of nice. And if you get a little bit rusty because you don't do power calculations every day, it's nice to pull up these 10-minute videos and just see how to do it. Of course, the software, the free software we have, would also help with that.
Yeah, so there's another question about torque, and if we calculate the torque requirement. In general, we don't calculate a torque requirement, so to speak. What we calculate is a belt pull, and we convert that belt pull that belt pull comes to us in pounds, because we're actually calculating, if you kind of drill down through, even through the CEMA calculations, they are assigning a certain amount of drag in pounds to each component of the system. So then we convert that drag in pounds to belt. That's a belt pull, and we convert that belt pull to a horsepower, because we know that 1 horsepower is always 33,000 foot-pounds per minute. And so if we know how many pounds we have, and we know how fast we're going, we can tell you how much horsepower you're going to need. So if we know how many pounds of drag we're going to need at the head, and we know how fast the material has to move, then we can convert that into a horsepower. So we don't necessarily work in torques, as I like to call them.
We just to add on to what Brian said, since CEMA talks about belt tension, and it's a convenient thing for conveyor designers and users to understand, we know tension is expressed in pounds in imperial units, and everybody talks about belt speed because that's going to affect the rate. As Brian said, pounds times feet per minute equals horsepower, because 1 horsepower equals 33,000 foot-pounds per minute. Once we start talking about torque, and I was doing this 27 years ago and I stopped, because when we talk about foot-pounds of torque, we talk about foot-pounds per torque, then we got to talk, what's the diameter of the pulley? What's the RPM of the pulley? And we talk about a whole different spectrum of things, which frankly are unnecessary, because conveyor designers care primarily about so many feet per minute of belt, a certain belt tension within the belt. Remember, I mentioned earlier that T2 plus TE equals T1. T1 is the magic number that the conveyor designer needs to calculate in order to buy the belt. So we're talking pounds of belt and feet per minute of the belt. Torque only complicates things. Can do it, but it adds complexity rather than removing it. So that's my 2 cents worth.
And that information that we just talked about in terms of belt pull and those calculations are also available on our website. The same place you would find the horsepower calculator. We explain that in a lot of detail, giving you all of the literal calculations that you need, and you can go into the minutia. And if you download our horsepower calculator, the CEMA horsepower calculator, then we actually call out the components and how each of those components look, and so there's a lot of good information in there to study.
And on that subject, feel free to grab the software that Brian mentioned. It's free. And one of our webinars, I want to say I should know this. I should have it memorized. I can even pull it up. Wait a second. Here we are. There we go. Webinar 102, rather than trying to use my memory, we look at together. Webinar 102 is 1 hour and 1 minute on how to use that program. So I draw your attention to 60 minutes of how to use the CEMA historical methodology using the downloadable software. Eventually, we're going to have a webinar put together on what we call the RCS, the Rulmeca computational suite, using the universal method. But for now, we know the tried and true historical method works. It's worked for a very long time. And that 1 hour webinar will help you through it.
And to use just further on the RCS, in order to use the RCS, I posted the link to the RCS in the chat feature. In order to use the RCS, you actually have to open up an account with our holding company. It's you have to fill out information and sign some privacy stuff. That's a European rule. That's not our rule. So
and it's free. It's also free.
It's free, but there are a few extra steps than just an email address that are required to get that software to you. And then once you have your account set up, you can use that as many times as you want, and it's pretty slick. It keeps all of the calculations that you've done. It keeps a running history of those, and it's a fairly powerful tool also. So I would recommend doing that.
It's got some bells and whistles that are beyond what I was able to put into the CEMA historical program when I wrote it back in the early 90s. So this is a similar version with an attitude. It's quite powerful, and we recommend it.
And then yeah,
so, did anything else come in?
Nope, I think that's it. So as soon as we get done here, we'll post this to our website, and then we'll probably push a newsletter later this month or early next month, just reiterating where it's at.
Thanks everybody for your time today. We sure appreciate you setting aside an hour to spend with us. We're all about motorized pulleys and helping people that have any conveyor issues. So once again, thanks for setting aside time to spend on this matter. And we hope that you'll keep safe and keep healthy. Bye now. Thank you.